Hey, welcome back to the channel. So in this video we're going to be learning about three different tests: the nth-term test, the integral test, and then P-series. So these are three different tests. Well, the first two are technically tests, and the third one is just a type of series. But these are all used to decide whether a series, an infinite series, converges or diverges. Okay, so these are used to determine convergence or divergence of an infinite series. Okay, convergence or divergence of an infinite series. All right, and there are actually a lot more tests and classifications. And technically, the nth-term test and the integral test are actual tests for convergence or divergence, whereas P-series is more of a classification of certain types of series, but you can still use it to determine whether the P-series converges or diverges. Okay, so we're going to start with the nth-term test, and it's actually, the full name for it is the nth-term test for divergence. So it's really used to determine whether an infinite series diverges. And make sure you've already watched my other videos on infinite series that comes before this one, so the geometric series and the telescoping series. Okay, so let's jump into an example of the nth-term test. Okay, example. Use the nth-term test for divergence. Nth-term test for divergence to show that the series is divergent or state that the test is inconclusive. Okay. So with the nth-term test for divergence, there's only two cases. Either the test tells you that the series diverges, or the test is inconclusive, which means the test didn't help you at all, didn't show you anything. Okay, so to show that the series is divergent, or state that the test is inconclusive, or state that the test is inconclusive. Okay, so I was kind of tripping over my words there a little bit. Sorry about that. What I meant to say is use the nth-term test for divergence. That's also just called the nth-term test. And we want to show that the series is divergent or state that the test is inconclusive. So for the nth-term test for divergence, there's only two possible cases. The first case is either the series is divergent or the test is inconclusive. That one would be the second case. Unfortunately, the nth-term test does not tell you if something converges, and it doesn't tell you if the series, if it does converge, it doesn't tell you what the series converges to. So it can only tell you whether if it's divergent or if it's inconclusive. Okay, so let's jump into an example. So example number 1. We have the series, which is the sum from n equals 0 to infinity of 1 over n plus 11. The sum from n equals 0 to infinity of 1 over n plus 11. Okay, so what we have to do here is the nth term test for divergence basically just means you take the limit as n goes to infinity of whatever's inside of your series, and then if that limit is not 0, or if the limit fails to exist, then the series diverges. Okay? So nth term test. Nth term test basically says if limit as n goes to infinity of a sub n is not 0 or fails to exist, the series diverges. Okay, and we're talking about the series sum from n equals 0 to infinity of a sub n. That series diverges. Okay, but then the weird thing about it is you would think, well, if the limit is not 0 or it fails to exist, the series diverges. So you would think if the limit was 0, you would think that it would converge. But that's not actually true. Alright, so if limit as n goes to infinity of a sub n equals 0, you would think that the series would converge, but it actually doesn't tell you anything. So if it doesn't tell you anything, it doesn't tell you yes or no about convergence or divergence, we say it's inconclusive. So if the limit as n goes to infinity of an equals 0, the test is inconclusive. And again, inconclusive just means it doesn't tell us anything. It doesn't tell us whether it converges or diverges. It doesn't tell us anything. So it's a very useful test if it ends up telling you that it diverges. But if it converges and you use this test, the test won't even tell you anything. It won't tell you that it converges. It won't tell you what it converges to. So it has a very limited use in determining whether the series diverges. Okay, so let's try to use that test up here. So basically we just take our a sub n is going to be what's inside of the summation. Okay, so this right here is going to be our a sub n, 1 over n plus 11. Okay, and then over here we're going to do the limit as n goes to infinity of 1 over n plus 11. Okay, that's our limit as n goes to infinity of a sub n, where a sub n is whatever's inside of our summation. Okay, and what's this going to go to? Well, our denominator is going to go to infinity, right? Because infinity plus 11 is still infinity. But then our numerator is fixed, so our denominator is going to become infinitely large, but our numerator stays small. So that's going to go to 0. So this whole thing is going to go to 0. And because it goes to 0, that's the case where the test is inconclusive. Okay, so how do we write our answer? Well, in my math lab, they just say the test is inconclusive because this limit equals 0. Okay, so the test is inconclusive. Okay, and that's literally all you have to write for your answer. Or on my math lab, it'll say the test is inconclusive because of what we just found. Because the limit as n goes to infinity of 1 over n plus 11 equals 0. So as you can see, in this case, the test didn't tell us anything, so we basically just wasted our time here. But the test still can be useful for other problems. So let's see another example. Maybe on this next one, we'll see a different case. Okay, so let's take a look at example number 2. It's got the same instructions. Okay, so for example number 2, we have the summation from n equals 1 to infinity of cosine of 17 over n. Okay, the sum from n equals 1 to infinity of cosine of 17 over n. So using the nth term test for divergence, we're going to be taking the limit as n goes to infinity of a sub n. Okay, so we're taking the limit as n goes to infinity of cosine of 17 over n. So what's going to happen here? Well, the denominator is going to go to infinity, but the numerator is fixed. So inside the cosine, this whole thing is going to go to 0. So really what we have here is cosine of 0. And what's cosine of 0? Well, at 0, you're on the positive x-axis on the unit circle, and the x-coordinate there is going to be 1. So cosine of 0 is 1. Okay, so what that means is the limit as n goes to infinity of a sub n equals 1. And because that is not 0, because that's not equal to 0, that means the series diverges. Okay, so let me write it in a different color. So this is not 0. So the series diverges. Okay, so if it's not 0, the series diverges. Right, because remember, back up here when I wrote it on the last problem, I said for the nth term test, the limit as n goes to infinity of a sub n, if it's not 0, or it fails to exist, the series diverges. If it equals 0, the test is inconclusive. So in the first example, we saw that because it equaled 0, the test was inconclusive. But in this case, it equals 1, which is not 0. So that means the series diverges. So it's actually a good test. It's pretty helpful, but it's only helpful in specific cases. It's very quick to do because you just do a limit of whatever's inside of your summation. And if that limit isn't 0, if it's anything else besides 0, then you know it diverges, which is really fast. So it's a lot faster than some of the later tests we're going to learn. Okay, so our answer is the series diverges. And it's a pretty useful test. Pretty useful. Okay, so I wanted to do one more example of the nth term test to prepare you for your homework. So let's take a look at example number 3. Okay, so for example number 3, we're doing the summation from n equals 1 to infinity of ln of 1 over n. Okay, the sum from n equals 1 to infinity of ln of 1 over n. So using the nth term test, we're going to be doing the limit as n goes to infinity of ln of 1 over n. So as n goes to infinity, this denominator goes to infinity, but because the numerator is fixed, that means 1 over infinity is going to go to 0. So this whole thing goes to 0, and then we get a weird situation. So here we have natural log of 0, or at least we're approaching that as a limit. I'll put quotes around it because ln of 0 is actually undefined. So then the question is, what is this approaching? So really what it is it's not ln of 0. What it is it's the limit as, we'll say, the limit as a approaches 0 of ln of a. That's really what it is. And maybe instead of calling it a, I'll just call it x to make it easy to plug into a graphing calculator. So you could say this is the limit as x goes to 0 of ln of x. And it's really the limit as x goes to 0 from the right-hand side. Okay? But probably the easiest way to see this, if you don't have it memorized, is to look at the graph of natural log of x. So you can go onto GeoGebra. Just open your browser, go to GeoGebra. Graphing calculator, open that up. And then just type in ln of x. And you can see as we approach 0 from the right-hand side, we can see that ln of x is going to negative infinity. Or if you prefer, we could have taken the original function we started with, which was actually ln of 1 over x. So if you prefer, you can look at that one. So you could look at it as ln of 1 over x. And then that one, as you go to infinity, ln of 1 over x is getting smaller and smaller. It's going down and further. So that's actually approaching negative infinity. Notice it just keeps dropping. So it's actually approaching negative infinity. Okay, but either way, you should be able to see that this is approaching negative infinity. So this limit equals negative infinity. And again, graphing is probably the easiest way to do that unless you have all those functions memorized in your head. Okay, so because that's negative infinity means the limit fails to exist. Even though negative infinity sounds like it's a number, it's not actually a number. It's going forever to the left, but it's not actually a number. Okay, so limit as n goes to infinity of our a sub n equals negative infinity, which this is the same as saying the limit fails to exist. The limit fails to exist. And remember, if the limit is not 0, or if it fails to exist, then that means the series diverges. Okay, so we're going to say the series diverges. Okay, so if that limit is anything besides 0, the series automatically diverges. Even if it's negative infinity or positive infinity or 10 or negative 13, anything. Anything besides 0, it diverges. Okay, so that's the nth term test. And that's pretty cool. It's pretty helpful and it's not that hard to understand. So let's move on to the next thing, which is called the integral test. Okay, so let's do a new example. Use the integral test, which we haven't learned yet. I'm going to teach that to you right now. Use the integral test to determine if the series converges or diverges. To determine whether the series converges or diverges. Okay, and we're going to do a couple examples of this. It's an important test. It's a lot more work than the test we just learned, but it's still important, so we're going to do it. So example number 1, we're working with the summation from n equals 5 to infinity of 9 over 7n plus 5. Okay, the summation from n equals 5 to infinity of 9 over 7n plus 5. Now, one nice thing about my math lab is these are multiple choice at the beginning, and you're going to be able to see they actually have some of the integrals already set up for you, which kind of should teach you the integral test just by looking at it. So it turns out that the integral test basically says you can convert a series, an infinite series, into an integral. You turn it into an improper integral, and then the value of that integral is going to tell you whether the series converges or diverges. Okay, so the integral test basically just says you convert this into an integral. Okay, so convert to integral, and generally your series is going to be in terms of n, so you're going to convert all the n's into x's. So convert to integral in terms of x. Okay, so now we're going to have the integral from x equals 5 to infinity, to x equals infinity. Well, x can't equal infinity, but you know what I mean. So it's really the integral from 5 to infinity of 9 over 7x plus 5 dx. So now how do we get this integral out of the series? Well, it's basically just the same thing, only, like I said, you replace your n, you replace every single n with x instead. And then you put a dx at the end, okay, and you turn a series into an integral. Now this doesn't always work, but it does work quite a bit of the time. And on my math lab, they talk about some of the integral test conditions that need to be satisfied. So if you have a weird case, some of these series can't be written as an integral, but this one can be quite easily written as an integral, so we're good here. Alright, so for this one, all we have to do now is do this integral. And if this integral goes to negative infinity or positive infinity, that means that the series is going to diverge. Whereas if it becomes a number, then that means the series is going to converge. Okay, so now we just go ahead and evaluate the integral. Okay, so evaluate the integral. And this is an improper integral, just like the ones we did earlier in our course. And to do this one, we want to use u substitution. So here we're going to let u be the inside of the composite function. Okay, so here our u is actually going to be 7x plus 5. Okay, so if u equals 7x plus 5, then du dx equals 7. So that means du over 7 equals dx. Okay, and then we can just go ahead and plug in du over 7 in for dx. So that's going to give us the integral of 9 over u times du over 7. And then we can factor out the 9/7 out front. So we have 9/7 times the integral of 1 over u du. 9/7 times the integral of 1 over u du. Okay, which is going to give us 9/7 times natural log of absolute value of u. Okay, but we got to get this back in terms of our original variable, which was actually x, right? Because we wrote the integral in terms of x. Okay, so u was 7x plus 5. So we're going to plug that back in here. So we're going to have 9/7 times natural log of absolute value of 7x plus 5. And then this is going to be evaluated from 5 to infinity, I believe is what we said. Yeah, from 5 to infinity. And that's from x equals 5 to x equals infinity. Okay, and then we're going to have to use a limit for the infinity. So instead of writing infinity, we're going to rewrite that as, we can call it c. And then we'll find the limit as c goes to infinity of this whole thing evaluated from 5 to c. And if you don't remember this, make sure you watch my other video on improper integrals because I talk about this. Okay, so we can go ahead and bring the 9/7 outside of the limit. So we have 9/7 times bracket, limit, as c goes to infinity of, well, plugging in c and 5, we're going to have ln of absolute value of 7c plus 5 minus ln of 7 times 5 plus 5. Okay? All right, so that's plugging in using the fundamental theorem of calculus, part 2. Okay, so what we got here is we're just plugging in the c first and then the 5 second. So the weird thing about this is we don't really care about any of this over here. This is just going to be 7 times 5 is 35, plus 5 is 40. So we have ln of 40. But over here, as c goes to infinity, this inside of the natural log is going to go to infinity. So ln of infinity is actually infinity. So this is going to go to infinity. And so this entire ln is going to go to infinity. So really we have, like, 9/7 times infinity minus ln of 40. Right? But that's just infinity. Okay? So that's infinity. So that means the series diverges. Okay? So what we say is the series diverges because the limit as x goes to infinity, I'm sorry, I don't know why I wrote that. Just had a brain fart. The series diverges because the integral from 5 to infinity of 9 over 7x plus 5 equals infinity. Okay, so basically when you're doing the integral test, if you get infinity or negative infinity, the series diverges. And if all this gets to be too much, you can go back to our formula sheet. If we open up our formula sheet on Canvas, then we can go ahead and look at, I think it's the 3rd page. I have infinite series on there, and maybe a little bit on the second page as well. But, it's usually in your week 2 or your week 3 module, depending on which course you're in. But it's that same formula sheet that I just keep coming back to, because it's really got everything from Calculus 1 and Calculus 2. Okay. So download, open file. Yeah, so this thing right here that I keep coming back to. So not on the first page, but on the 2nd page and the 3rd page. The 3rd page particularly actually have all these different convergence and divergent tests for series. So we already did the nth term, we already talked about geometric, and right now we're talking about the integral test. So the integral test basically just says it converges if the integral from 1 to infinity, or in this case the integral from 5 to infinity converges, and it diverges if the integral diverges. And for an integral to diverge, that usually either means it's negative infinity or positive infinity. And the only comments is the function f obtained from a sub n equals f of n must be continuous, positive, decreasing, and readily integrable. But all that stuff is done for us on our homework, so we don't have to worry about this too much. So basically, if your integral is an actual number, then that means that the series converges. However, if your integral is infinity or negative infinity, then your series diverges. Okay? So this series diverges because the integral was infinity. And it would also diverge if the value of the integral was negative infinity. Okay? But you probably already guessed that. Because infinity and negative infinity are almost the same thing, they're just off by a minus, and they live very far from each other. Infinitely far from each other. Okay. Alright, cool. So you're going to have a few of these in your homework. I'm not going to do one of each type because there's too many of them. But I did want to do another problem. In particular, I wanted to show you one that does converge. Okay, so we can see one that converges. So for example number 2, for the integral test, we want to use the integral test to determine whether this series converges or diverges. And here our series is the sum from k equals 4 to infinity of 1 over 5 e to the 2k. The sum from k equals 4 to infinity of 1 over 5 e to the 2k. Okay, so basically all we do is, just like in the last problem, we replace the letter k with x, and then we turn it into an integral. Okay, so it literally looks the same, we just replace the summation symbol with an integral symbol, and now it's in terms of x. So it's still going to go from 4 to infinity, but we're going to have 1 over 5 e to the 2x dx. So you add in a dx afterwards, otherwise you wouldn't be able to do the integral. Okay? And then you just go ahead and integrate it. Okay, so how do you integrate this one? Well, you can bring out the 1/5. You can factor that out front. So we have 1/5 times the integral of, I'm going to go ahead and write it as e to the negative 2x dx. Because remember, if you move a positive exponent over the division bar, it becomes negative. So if I move that e to the 2x upstairs, it becomes e to the negative 2x. Okay, and then here I can just do u substitution. So I'm going to let u equal the inside of my composite function. So here u is going to equal negative 2x, which means du dx equals negative 2. And that means du over negative 2 equals dx. Okay, so we can go ahead and plug in du over negative 2 in for dx. Okay, so we have 1/5 times the integral of e to the u times du over negative 2. Alright, and then from there we can factor out the negative 1/2. So we're going to get negative 1/2 times 1/5 out front. And then we have the integral of e to the u du. So multiplying those fractions straight across, we get negative 1 times 1 on the top, and negative 2 times 5 is 10 on the bottom. So we're going to have a negative 1/10. And then remember that the integral of e to the u is just e to the u. Okay, so we're going to have negative 1/10 e to the u. But then in this problem, u was negative 2x. Okay, so this is going to be negative 1/10 e to the negative 2x. Okay, and then now that we've gotten it back in terms of x, we can go ahead and plug in the original values of the integral. So we went from 4 to infinity. So we're going to go ahead and do that. So we're going to be evaluating this from x equals 4 to x equals infinity. Of course, x can't actually equal infinity because infinity is not a real number. So once again, we write it as a limit. So we write this as the limit as c goes to infinity of -1/10 e to the negative 2x, which goes from 4 to c. Okay, and then we just go ahead and plug in here. So if we bring the -1/10 out front, we're going to get -1/10 times the limit. Well, let's go ahead and distribute the limit. Let's save some time here. So if we distribute the limit, we're going to get -1/10 times limit as c goes to infinity of e to the negative 2c minus e to the negative 2 times 4. So all I did in that step was I factored out the -1/10, and then I plugged in, I plugged in the top number, which was c, and then I subtracted it, evaluated the bottom number, which was 4, and I also brought the limit on the inside. Hopefully that's not too much though, because we've done a lot of problems like this on these videos. Okay, so now we just plug in infinity here. But remember, e to the negative 2c is actually the same as 1 over e to the positive 2c. So if we take the limit as c goes to infinity of 1 over e to the 2c, this denominator is going to go to infinity, right? That's going to go to infinity. But then 1 over infinity goes to 0. So this whole thing is going to go to 0. Which means we really have a -1/10 times 0 minus e to the negative 8, right? Because negative 2 times 4 is 8, negative 8. Okay, so, and then we can simplify this a little bit. The minuses are going to cancel out. Okay, so if we cross out the minuses, then we're going to have 1 over 10 times e to the negative 8. And the way they write it on my math lab is they write the e to the negative 8 in the numerator, and then the 10 in the denominator. Okay, so the final answer is e to the negative 8 over 10. But that's the answer for the integral. So they're going to ask you to write that down, type that in, rather. But the question is, does this converge or does it diverge? Well, remember, unless you get infinity or negative infinity for the integral test, this is going to converge, okay? So because this one isn't negative infinity, it's not positive infinity, this converges. Okay, so the series converges. And that's by the integral test. So they are going to ask you for the value of the integral. But just keep in mind that the value of the integral might not actually be the value of the sum of the infinite series. That's not always the case. Okay? And then you have a couple more like this in your homework. And I recommend using view an example if you don't remember everything. But the basic idea is you're just going to be plugging in, and you're going to rewrite your series as an integral, and then you just plug stuff in. So I think I'm just going to help you set up the next problem, but I'm not going to do the whole thing. Okay, I just want to help you set up the next problem for your homework. So that was example number 2 for the integral test. This next one is example number 3. Okay, so for example number 3, we have the sum from k equals 1 to infinity of 2k plus 2 all over k squared plus 2k plus 7. Okay, so the sum from k equals 1 to infinity of 2k plus 2 all over k squared plus 2k plus 7. Now I'm just going to help you set this up, but I don't want to take out all the fun out of it. So I'm going to let you work the rest of it out on your homework. Keep in mind on your homework it won't be exactly these same numbers, but it'll still be a similar problem, just with different numbers. Same setup, different numbers. Okay, so what we got here is we're going to convert this into an integral. So what's this going to look like as an integral? Well, we're going to replace every single k we see there with x instead. So all those k's are going to become x's. And instead of the summation symbol, we have the integral symbol. So now we have the integral from x equals 1 to infinity of 2x plus 2 all over x squared plus 2x plus 7, okay, dx. The integral from 1 to infinity of 2x plus 2 all over x squared plus 2x plus 7 dx. And then that's the basics, but you might not be sure how to do this integral, so I did want to show you how to do that. So this seems like a tough integral, and you might think, oh, well, do I have to do partial fractions, or do I have to do long division? But it's actually not that bad. You can do this one by u substitution. So I wanted to point that out to you. So what you're going to do here is you're going to let u be the denominator. And the reason you want to let u be the denominator is the derivative of x squared plus 2x plus 7 is actually 2x plus 2. So that's the secret for that one. Okay, so we let u equal x squared plus 2x plus 7. Okay, and then we're going to have du dx equals 2x plus 2. Alright, and then the problem goes on and you work through it and you can evaluate the integral the same way we did the other ones. So I'm not going to go any further than that, so I'll just put ... here. But I kind of spilled the beans there, so now you know how to do that integral, because that one's a little bit tricky. But you can follow the steps of the other ones to finish that problem. Okay? Alright, so that finishes the integral test. So the last thing I wanted to talk about on this rather long video is P-series. So P-series are actually a lot easier than the integral test. So let's talk about P-series. So P-series, probably the easiest way to learn about it is by example. So I wanted to show you something that's a P-series. P-series just means you have the sum from n equals 1 to infinity. It usually starts at 1 because otherwise you'd end up dividing by 0. Of a over n to the p. And it doesn't have to be a over n to the p. It could just be 1 over n to the p. In fact, it's usually 1 over n to the p. In fact, I'll just leave it that way. But it can also be any constant over n to the p, and it'll still work. So it turns out that with P-series, once again, you can look on your formula sheet. It's in there. So with P-series, the sum from n equals 1 to infinity of 1 over n to the p converges if p is greater than 1, and it diverges if p is less than or equal to 1. Okay? So converges if p is less than 1, right? And wow, I'm having the worst day and saying the wrong thing. So it converges if p is greater than 1, and then it diverges in the other case. So it diverges if p is less than or equal to 1. Okay, converges if p is greater than 1, diverges if p is less than or equal to 1. And if you forget these, like I have been doing, just look on your formula sheet. This is on the 3rd page under P-series. converges if your exponent p is greater than 1, and it diverges if your exponent p is less than or equal to 1. Okay, so I wanted to do a quick example of p-series. Even though they're very easy, they're just very helpful. They're super easy to do, and they're very helpful. So basically, you're just looking at your exponent. If it's bigger than 1, it converges. If it's less than or equal to 1, it diverges. Okay, so example. New example. Does the series converge or diverge? Does the series converge or diverge? And I know it's a simple question, but on my math lab, it's actually going to be multiple choice. So you're going to need to choose the choice that says the right sentence, because each choice is actually an entire sentence. So for example number 1 here, we're going to jump straight into a p-series. So this one is the sum from n equals 1 to infinity of 3 over the square root of n. So you might be wondering, well, how on earth is this a p-series? I see a square root, I don't see a power. Well, remember, the square root is the same as the 1/2 power. So this is actually the same as the sum of 3 over n to the 1/2 from n equals 1 to infinity. So here we can see our exponent p is actually going to be 1/2. Okay, so our exponent p equals 1/2. So this is p-series where p equals 1/2. And remember, 1/2 is less than or equal to 1, which means that the series diverges. Okay? Okay, so the series diverges. Because remember, if p is less than or equal to 1, the series diverges. If p is greater than 1, the series converges. Okay, so let's jump into another one. Those are very simple. The p-series ones are a lot of fun because they're so easy to understand. Okay, so number 2. They're easy to understand and they're useful, I should say. So number 2 is going to be the sum from n equals 1 to infinity of -49 over n to the 3. Okay, the sum from n equals 1 to infinity of -49 over n cubed. So the thing about this is it's still a p-series, because what you can do is you can factor out the -49. Okay, so you can actually bring the -49 out front. So we get -49 times the sum from n equals 1 to infinity of 1 over n cubed. So now it's in the form 1 over n to the p. And here we can see that p, this is a p-series where p equals 3, but 3 is greater than 1. So because 3 is greater than 1, that means this converges. Okay, so it converges. All right, and then notice for the test for the p-series, it doesn't tell you what it converges to, but it tells you that it does converge. Okay, so the series converges. And that's going to be our answer. And what about the -49? Well, any number, any finite number times another finite number is going to mean the series still converges. So you multiply, say the series converges to 5, -49 times 5 is still a number, still a real number, so it still converges. Okay, so this constant out front isn't going to change anything. It's still going to converge. We don't know what it converges to. We don't know what the sum of the series is, but we do know that it converges because it's p-series. Okay? Now you might think you're good on all your homework, but I did want to show you one more tricky one. In fact, I wanted to show it to you right after the one we just did. So just one more example. Example number 3 here. The sum from n equals 1 to infinity of negative 1 over 7 to the n. The sum from n equals 1 to infinity of negative 1 over 7 to the n. And they're asking, does it converge or does it diverge? So you might be thinking, oh, well, is this P-series and the exponent is n? That doesn't make sense. No, this is not P-series. That's the trick about this one. This one's actually geometric series. This is geometric series, not P-series. Now, how can I tell the difference between a geometric series and a P-series? Well, remember, with a P-series, your exponent has to be a fixed number. So looking at these, here the exponent was 3 for example number 2. For example number 1, the exponent was 1/2, and the n was actually the base. So for a P-series, n is the base. See here, the n is the base for each P-series, whereas for this one, n is the exponent. Okay, so how do we tell the difference? Well, geometric series means n is exponent. So n is the exponent for a geometric series. Let me just write out the full word. Whereas for a P-series, n is the base. Okay, so that's how you tell the difference between a geometric series and a P-series. N is the exponent for geometric, n is the base for P-series. And with that information, oh my gosh, what did I do here? I messed up my window. Okay, there we go. So because it's a geometric series, we're going to use the information from our previous lesson on geometric series. And remember, for a geometric series, it's in the form a times r to the n. Okay, so we want to write it in the form sum of a times r to the n. Okay, sum of a times r to the n. So what's that going to look like? Well, we're going to have the sum from n equals 1 to infinity of, here we can see that a is going to be negative 1, and then r to the n is going to be 1/7 raised to the nth power. Okay, so a is negative 1, and then r is 1/7, and this is negative 1 times 1/7 to the nth power. And then how do we determine if a geometric series converges? Well, we just look at r. So here r actually equals 1/7, which is less than 1. And remember, if r is less than 1, that means the geometric series converges. Okay, so this converges. And that's because it's geometric and r equals 1/7, which is less than 1. And that number 1/7 is also called the ratio. Okay, so this number 1/7 is called the ratio. I just wanted to point that out because on my math lab sometimes they say the series converges because it is a geometric series with ratio r equals 1/7. So r is the ratio, and that's 1/7. Okay, so that's our last example. So thanks for watching all the way to the end. Have a good day.